Hey, Chemistry Honor students. I apologize for this podcast coming up really late. My computer has been crashing a lot in the past week, and I will hopefully I have resolved this problem, or I have to get a new computer. All right. So over here, this is your podcast number 2 of Unit 2, and these are the topics that I will be covering. This corresponds to everything from chapter 14.1 to 14.3. All right? Okay. But before I get into the factors that affect gases and their relationships to each other, I first want to talk about math. So you guys already know much of this. In direct relationship, you know that as x increases, y increases. So if I had a data for x, kind of like 0.5, 1, 2, 3, 4, my y value would increase in proportional to that, and so it would look something like 0.5, 1, 2, 3, 4. So if I were to now graph this, I would have 1, 2, 3, 4. This is my x-axis, and this is my y-axis, and here's my 1, 2, 3, 4, 1, 2, 3, 4. So if I were to graph this, I have 0.5, 0.5, 1, 1, 2, 2, 3, 3, 4, 4, and here is my line that corresponds to it. So if I see a line like this or a slope like this, I know this is a direct relationship. So now if I were to put this into an equation form, I know that my slope equals my y over x, and so my y1 over x1 equals the slope, which also equals to y2 over x2, and so my equation right now, equation overall would be y1 over x1 equals y2 over x2. And please note that in a direct relationship that the variables x and y are on one on top of, on top of the other. But in an inverse relationship, you have an xy value, you have 0.5, 1, 2, 3, 4. Inverse will be 1 over 0.5, which comes out to be 2. 1 over 1 equals 1, 1 over 2 equals 0.5, 1 over 3 equals 0.33, 1 over 4 equals 0.25. So now if I were to graph this, I have 1, 2, 3, 4. This is my y-axis. 1, 2, 3, 4. This is my x-axis. My 0.5 on the x would equal to 2. 1 would be 0.5. Sorry, 1 will be 1. 2 will be 0.5. 3 will be 0.1. 4 will be 0.25. And so now I have a graph that looks like a exponential decay. So this, whenever you see a graph like this is an inverse relationship. Please note that this is an inverse relationship. Okay? So now this graph is a little hard to analyze because it's really hard to know the slope of this graph at various points. So to make it a little bit easier, I am actually going to I'm going to crunch some of this data. And because I don't have any room over here, I'm actually going to go here. I apologize for not making room enough room for that. So I'm actually going to do 1 over y value. And so this will be 1 over 2, which comes out to be 0.5 again. 1 over 1, which comes out to be 1. 1 over 0.5, which comes out to be 2, 1 over 0.33, which is 3, 1 over 0.25 equals 4. So now, as you can see, if I were to graph x versus the 1 over y, I have a direct relationship once again. So if I were to graph this, my axis will be x and 1 over y. Here's my 1, 2, 3, 4, 1, 2, 3, 4, and I have 0.5, 0.5, 1, 1, 2, 2, 3, 3, 4, 4, and now I have a direct relationship once again. So if you were to graph instead of x versus y in an inverse relationship, but x versus 1 over y, you get what it looks like a direct relationship. So over here, the slope will once again be 1 over y over x, and that's a little messy, so I'm just going to put 1 over x times by y. And so I have 1 over x times by y equals the slope, x1 times by y1 equals the slope, which also equals to 1 over x2 times by y2. This is a little bit messy, so I'm actually going to write this. X times by y1, x1 times by y1 equals 1 over slope, which also equals to x2 times by y2, which also equals the slope. So now I have a x1, y1 equals x2 times by y2, and this is a formula for an inverse relationship. Please note that x and y are next to each other. X and y are side by side in an inverse relationship. So the variables are side by side when they are in an inverse relationship. They are one on top of the other in a direct relationship. Just to cover the symbols for the gas unit, when I say amount of gas, I'm actually talking about the number of particles, and because particles are really small, we're going to count them in groups of moles. So the unit for N is moles. Volume has a unit of liters, and in that we're just talking about how much space that gas takes up. And temperature is always going to be in Kelvin. Please, no Celsius. Please do not use Celsius. Do not use Celsius. And when I talk about temperature, I'm talking about the speed, the average speed of the particles, of the gas particles. So now let's talk about the relationship between volume and pressure. Here's my volume, and the gas particles are moving at a specific speed, and they're bouncing off the wall to create the pressure against the inner wall of this container. If I were to decrease volume by pushing this piston down, they're still going at the same speed. The number of particles is the same. However, they're hitting the inner walls of this container more often because there is less space. So over here, as volume decreases, pressure actually increases because they are hitting the inner wall of this container more often. However, please note that the constant in this relationship, what is not changing is that temperature is not changing, the speed of the molecules have not sped up or slowed down, and the number of particles has not changed. So if I know that this is an inverse relationship, then I know that V1 times by P2 must equal V1 times by P1 must equal V2 times by P2. And this is called the Boyle's law, which is also up here. So now let's talk about the relationship between pressure and temperature. So this box shows you a picture of the particles going at a specific speed. And as you can see, the arrows are a little bit smaller, indicating that the particles are not moving as fast. However, if I were to heat up these particles, the particles are moving much faster, which is indicated by the longer arrows. But as you guys can see over here, the number of particles have not changed, so it is constant. And what also has not changed is that the volume of the container is also constant. So the only two things changing in this phenomena is the speed of the particles and therefore the amount of pressure causing the inner walls of these containers, because the particles are hitting against the inner walls of the container more often and harder. So as temperature increases, the particles speed up, they're hitting the inside wall of the container more often and harder, and so now you see a direct relationship. In a direct relationship, we know that the variables are one on top of the other. T1 over P1 equals T2 over P2. And this is okay. And you could also write it as T1 over P2 over T2. And the reason why is because we're just doing proportions here. And so either one will work perfectly fine.